Maria. I have just a few minutes, but I want to give you an insight about what we developed, or the motivation behind the development of our knowledge graph inside the vast project. And I'm here to represent a sort of a large group of people that contributed to this model and to this idea. And I like to say that this is a sort of shared thinking among many people. I don't know how to. Okay, to go on. First of all, the idea of our knowledge graph is based on the fact that we have to represent many different aspects. And in particular, we have to deal with the different period of time, in a sense, because we wanted to take care of the so-called past of values and the so-called present of values, in the sense that we have different people and different sources that need to be represented inside our knowledge graph. What we call past of values is something that is related to the values, to the moral values we analyze in the vast project that are taken from sources. We have three pilots. One is the ancient Greek drama, one is the scientific texts from the 17th century, and one is the folklore and the fairy tales. So the idea is that we have to take from these sources the occurrences of these values, and we want to represent this. In this process, we involve the experts that are members of our consortium that have been involved first in the definition of a common vocabulary, so that we have a common ground for describing things. And then with the annotation process to recognize explicit and implicit occurrence of these values inside the considered and selected sources. But in addition to this, the model and the repository has to take care of the so-called present of values, where the involvement is based on the engagement of people, of common people, of visitors to the museums, students that are engaging in our activities, the spectators to theatrical plays, that receive a sort of stimulus, that are part of a certain experience, and they want to, and they are asked to provide a feedback, what they receive, which are the values they recognize in what they see and what they read and what they are experiencing. And all these things are obviously, possibly as an opposition, as something that can be contradictory. So one of the things, the core features of our knowledge graph is already being said by George, our coordinator, is that we want to take care of all these things in the knowledge graph. So we don't want to provide a common understanding, a shared understanding. We want that all the persons involved, engaging in the project, can have their own perspective, and this perspective has the dignity of being recognized and being represented inside the knowledge graph. So we arrive to the model. The model is quite complex, but it is based on the idea that we have four main areas of representation inside the graph. The user part is quite common, and I don't want to focus on it because it is the part related to the representation of the metadata about the persons, of the people involved. Then it's more interesting to focus on the other three aspects: the concepts, the activities, and the artifacts they produce. About the concepts, this is the part mainly related to the past of values, because here is where we store the common vocabulary, the concepts that are related to the values, and to the fact that we have two challenges here. The first one is about the need to interlink things, because it's true that we use a common vocabulary, but it is also true that the keywords used has been enlarged and extended by recognizing also all the keywords received by the people participating in the activities. So people use different terms also to describe the same thing, and we need to map them. We need to have a sort of space where the terminology is, in a sense, managed so that we can recognize similar things and we can distinguish different things. So there is a challenge that is related to the mapping of the terminology. Another challenge is that we need a sort of reference framework for being also communicated to the outside person of the project. And we use the Schwarz theory about values. that is quite famous and quite recognized as relevant. I'm a computer scientist, then I say what I've heard by the experts on this, but the thing is that this is the core part of our model. The other parts are related to the representation of what we produced. And what we produced is about the activities, that is what we have done with the people, with the communicators, with the people that have been engaged in the project. And in particular, the model recognizes the phases and the elements that characterize the methodology of our project. That is probably one of the core contributions of the project. So the idea is that we have events. Events are articulated and can be described across the steps that characterize this event, and the stimuli the people receive, because are all relevant elements that characterize what we do. And the idea is that also the activities can be something that people see and want to reproduce. And reproduce means that you want to have guidelines, you want to have things that you can use as reference, but you want to adapt it to your own case. So the idea is that the model must be flexible enough also to receive things that have been produced in activities that are not fixed and not statically defined. And finally, the artifacts. The artifacts are the products, the things that have been produced during the activities. And this can be very heterogeneous because in the project we have developed technologies for digitizing things. So sometimes they are natively digitized because we have digital games, we have tools that are directly used during the activities, but sometimes the process is more conventional, more traditional, in the sense that the people works on the paper, people discusses among them, and finally what they produce is somehow digitized. And this process can be, again, very heterogeneous. So we have questionnaires, we can have interviews, we can have maps, we can have the result of games. All these things produce knowledge to us. And we have mapping this again, because we want to produce statements. These statements can be, in a sense, paired with the tool, because the tool has the mechanism for translating what they receive as input and produce statements to be stored in the knowledge graph as output. But some other times, the translation process, the input process of the statements to be inserted in the knowledge graph is in the hands of the curator, of the person involved in the organization of the activity. In both cases, the results comes out as statements that are inserted in the project, in the knowledge graph, sorry. I close my talk with some hints about the size of this knowledge graph. It is implemented as a GraphDB, or better, it is more than one GraphDB that are, of course, interlinked. And the number of annotations are the result of all the activities, so are the results related to the person, the human persons that have been involved in the project. Till now, because digitization activities are still ongoing. And mainly the three knowledge graphs, in addition to the core one, are about the annotations coming out from the past of values and the survey data that are the questionnaires collected from the people, and all the digitization tools that I briefly described so far. And that's all. Okay.
Okay, so I'm going to introduce to you the InTaVia knowledge graph, and I'm going to focus a bit on the system architecture rather than the model itself. So what you see here is basically where so what we will talk about, namely we on the left side have the data, so the object databases, the person databases, the unstructured biographies that we used. And we are then using prefect workflow components, pipeline components, basically to convert the data and ingest it in a triple store. And then in front of that, we have a SpAQL endpoint that we use to have a garlic API for, we changed that for a fast API, and a custom library that is processing that. And then on the right side, we have basically the front-end components that consume these API endpoints to allow for visual analytics and data curation, and in the end also story editors and story viewers. Yes, so I'm going to give you a quick overview on what the knowledge graph contains. So currently it has about 260,000 person proxies, so that's not distinct persons, but it's one information, basically one data source on a person. Then about 35,000 place proxies and 170,000 cultural heritage object proxies. Across the data sets, so we have, I guess, Eva already introduced that, we have 4 different biographical data sources. This is the APIS on the left side, which is the Austrian Biographical Dictionary, Biography Sample right up, Biography Net, Dutch data bottom left, and the Slovenian data bottom right. And what we see here is that basically only the Austrian data has institutions. The biography net is by far the biggest, with over 200,000 person proxies, and the SBI data is the most smaller data set that we have, and the biography sample data has by far the most events per persons. We have not very similar data sets actually. So what you see here is the shared persons across the data set. So obviously the Austrian and the Slovenian data sources share a lot of entities, over 500, but the rest of them actually don't share a lot of data. This is what we see here is the stacked events histogram. We colored that in green for the biographical events and blue for the cultural heritage object events, which are basically the creation of a cultural heritage object. And what you see there is a huge spike in the 17th century, which comes from Dutch data, Dutch artists who have a lot of entries in Europeana and Wikidata. And the other events, so the biographical events, are starting in the 18th century, and they're coming mostly from biography sample and the Austrian dataset. We obviously have a huge gender imbalance in our data sets coming from the old sources. So these biographical dictionaries have been all written throughout the last centuries. In the Austrian case, we only have 900 females, where we have more than 17,000 males. But this is for actually all of the data sets. For BiographyNet, there was an error in the retrieval of or in the ingestion actually of the data set. That's why we have only 600, 800 gender information here. So this is not really useful. But for all the others, we see that there's a huge gender imbalance. This is also, if we put that on a timeline, we see here in the Austrian case, in the bottom left, in the 10 years average, the imbalance is changing a bit, so it's getting a bit less worse in the 19th century, where it is much worse in the 18th century. Yes, if you have a look at the number of events per person, so in the left chart you see including cultural heritage objects, in the right without the cultural heritage objects. We see that there is some persons who have more than 2,000 events in our data set that comes from the cultural heritage objects. So where is very famous artists, where all of the artists of the artworks are in Wikidata or Europeana, or it's also people who wrote lexicon articles, for example. And when you have a look at the right side, we see that biography sample, so only using the biographical events, has the most events per person. Putting all of the knowledge graph in a social network, just to have a look at how big the data is. We have here more than 300,000 nodes and more than 800,000 relations, but we see that a lot of the data is still unrelated, even though we enriched it a lot and tried to pull more data in. The big cluster in the middle is Austrian data. The cluster on the right is the BS, the Finnish data, and the smaller one is the SPI data. And a lot of the Dutch data is actually still unrelated to the rest. So how does our workflow look like? So we had different data sources. So Slovenian data, for example, is encoded in TI. The Finnish data was already in CaTCH, and Austrian data came from a JSON API. We use then conversion pipelines, either running on local machines or in the cluster in a prefect pipeline for the Austrian data to create CaTCH or data CaTCH encoded named graphs, ingested those named graphs in the triple store, and we had then prefect pipelines enriching these data sources, for example, finding same as links to create entries in the InTaVia harmonized named graph that I will show in a moment, or adding more data from Wikidata or Europeana, the cultural heritage objects, for example. And then we have SPACUL templates, basically SPACUL queries that are used by the REST API to query the triple store and convert the data that is returned from the triple store in a deeply nested JSON and give that to the requesting client, which is in most cases our front-end application that I guess you already saw. So I'm going to leave that out. We are using a custom library to create from the flat data that is returned from SPACUL queries a nested JSON representation. Yeah, the data model itself, the IDM RDF, is based on CaTCH 7.1, and it's using the BioCRM extension for roles that is developed by the Finnish colleagues in the consortium. It uses RDF named graphs for separating the sources, all of the sources, so the original sources like the biographical data sources, but also those data sources that we created via enrichment. It uses EDM-inspired CRM native modeling for cultural heritage objects. This has a primary mapping from IDM to EDM, and we're using a proxy model for connecting the entities. I'm going to show that in a moment. Prof O for provenance and BibFrame for the bibliographic data. So a typical IDM RDF event construction looks like, most of you will know from CaTCH. So we have an entity connected via a role to an event, and the second entity or even more entities also connected via a role to this same event. And then we use P4 as time span and P7 took place add to add the time spans and the places to these events. So now to the separation of the data in the named graphs. So in the upper graph, you see an example of a Europeana construction on Adalbert Edelfelt, who created a CHO object. And at the bottom, you have the same person from the biography sample graph, so the Finnish data. And in the middle, we have the InTaVia shared entity graph, which basically only has a provided entity which points to the source entities in the other named graphs. So this provided person is basically the way we then connect the different data sources together. And this entity linking works via same as links. So in this case here we have the biography sample data, a person called Giuseppe Acerbi. We also have this Giuseppe Acerbi in the Austrian data, and in the Austrian data we have the G&D ID as the same as in the biography sample data we have Wikidata. And what we do is then in a prefect enrichment flow, we query the Wikidata SPACUL endpoint for the G&D and get the Wikidata identifier. And this is how we know that both the Giuseppe Acerbi from BS and from Google are the same. And that's then what we put into the shared entity graph, namely that these two are the same person. Yes, the IDM JSON that we're delivering via the API is a kind of a simplified version of this very complex RDF model. We have basically some parameters as such as the gender and the name and alternative labels, and then we have a node history, which is basically an array of all these events that are in the triple store. I'm going to leave that out. So then for a small example, so this is on the left here, the Swagger endpoint of our API that you can query actually, that is open accessible. And we have here events endpoints, entities endpoints, vocabulary endpoints, and some statistics endpoints to retrieve statistics from the knowledge graph. And if you now, for example, want to query for the Acerbi that I just showed you, what you will get is basically a list of entries that are returned. And there's an Acerbi Enrico. There is also this Acerbi Giuseppe that I just had in the example. And there you see that, for example, the linked IDs are from biography sample, but also from the Austrian data and from the GLD and also from VIAF in this case. And then we have here his occupations that are coming from the different sources. And we have here alternative labels and then a list of relations. And if you look at the same entry in the front end, so this is now the live view of the front end, you see that the front end basically consumes that API and gets all the data nicely rendered. This is here the Wikidata links, biography sample, the gender, and then the different occupations coming from the two dictionaries. And here then the events that are also coming from the different dictionaries. And what you see here is that we have two birth events for the same person, because this is because in biography sample, the birth date is only 1773, and in Austrian data, we have an exact birth date. You see also here the biography that's coming from the Austrian data. We are not unfortunately allowed to publish the finished biographies. That's why there's only the Austrian one. Yes, so a few things we are still only have demonstrators for that we still wanted to achieve or still working on. One is that we're working on the Schlögl validation for the data ingestion so that we get better validated data ingested in the knowledge graph. The second thing is that we want to have a workflow where the data is basically ingested via GitHub repositories. This would allow, so the validation, the Schlögl validation is then running in GitHub Actions, which would allow or will allow everyone who is able to build RDF data that is that can be validated against our Schlögl constraints is able to do a pull request against our ingestion repo, and if someone from the consortium basically allows him or validates the merge, then the data will get merged and pushed to our knowledge graph. Yeah, these prefect pipelines will then also, the enrichment prefect pipelines will also commit the new data to the source data repo. And then all of these named graphs can basically also be downloaded directly from the GitHub repository. A few of the challenges, and that's also in the end of my presentation, that we found was the accuracy versus usability. So this is especially pointed towards provenance of the data. So there's a lot of provenance information generated during these enrichment pipelines. And it's not very feasible to keep all of that. And in our case, it was especially challenging to keep the different languages. All the vocabulary entries, the types, and the definitions are all in different languages. And still are actually for most of the things. Then there was a problem with the duplicates that we tried to come by while using the CMS solution, and also the performance of the APIs or the performance of the triple stores when dealing with large amounts of data separated in different named graphs. So these are the repositories. Everything that we created, including this presentation here, can be found in the InTaVia GitHub organization. And the second one is the API endpoints, and the third one is the front-end application. Thanks.
So yes, thank you. I'm Pasquale Lisena, and I am the representative of the project Odeuropa. That is a project that is spanning different, a consortium of different partners from all over Europe. I'm actually from France, but in the project there are people from Slovenia, Italy, Germany, the Netherlands, and the UK. So, what is this knowledge graph about? Is of course a graph about cultural heritage, and our starting point is the fact that we have centuries of collective smell memories. Okay, so in the past, people that have had olfactory experiences had particular sensation, emotions, or whatsoever, and all these memories are part of our heritage, and a lot of information can be get from this heritage. We can have questions like what was the most frequent smell in London in the 18th century, or what emotion was associated with the floral smells in the centuries, or which kind of smell was able to smell a soldier during the Waterloo battle, for example. Okay. And where this information are coming from, in particular, they are coming from text and all books, novels, documents, essay, etc., even laws coming from the past, in which these smell experiences are quite well described, and also images. In a lot of paintings, there are olfactory references that are quite well identifiable, because there is someone smelling something or having some gesture that remind us about this kind of smell, or there are quite evident smell sources represented. So we extracted information from text and from images, and realized that the Odeuropa knowledge graph, that is a tool that we use to, of course, for querying information, so as an aggregation of different data that we are able to visualize, but also for running, and this is the quite next future, some AI tool on top of it. Yes. Okay, so how do we did organize this information? We realized an Odeuropa data model that has been realized on purpose by the collaboration between us computer scientists and the expert of the domain. And we decided to extend CaTCH CRM, that maybe some of you knows. This also for two reasons mostly. One, for fostering the usage of this model in the heritage domain that is already used to CaTCH CRM, and also because this model represents things as events, and given that you don't know what to represent actually in the about the smell, because it's a non-tangible part of our heritage, so it's very hard to identify it precisely. We decided to group the information around the two main events. One is the smell emission, Okay, so actually the proper moment, the proper event for which the smell is generated, and the olfactory experience. That is all the olfactory experience carries all the subjective part of the smell. All these two elements that are connected to this central smell event are part of the Odeuropa data model core, to which then we add to the smell emission, we connect the smell source, the smell carrier, etc., etc. So all the things that are, how to say, clear and objective. And to the olfactory experience, we have the qualities that are the adjectives basically that have been used to describe the smell, but also the gestures, emotion, etc., etc. Together with the Odeuropa data model, we produced some control vocabularies using the SCOS syntax. In particular, we are speaking about some multilingual vocabularies that have been realized on purposely during the project. And here the numbers are a bit outdated. Actually, we enlarged recently these vocabularies, but we have big vocabularies about olfactory objects. So everything that can smell, basically, or we can find that is somehow connected to smell. A vocabulary is about olfactory gesture, and one about fragrance spaces. The cool things about these vocabularies that we realized in order that these vocabularies have a hierarchy. That means that we have the the plants, and then we know that flowers are part of plants, and then we know that the rose is part of flower, etc., etc. But we have also bridges between vocabularies. We know that the fragrance space of a stable is connected to the smell of cows or of horses in general, okay? So we have all these kind of links between vocabularies, and we have a lot of interlinks with Wikidata and Econ class inside. Moreover, we converted a number of existing taxonomies and smell classification that were already available and are already used in the chemical industry, in the perfume industry, etc., etc. And we transformed it in a way that the machine can read and process. So together with the description of a smell, we decided to include in the knowledge graph also all the metadata from the sources from which has been extracted, okay? So that means that a specific smell, so a combination between a smell emission and olfactory experience, have been described in a book, for example, that have a name, a specific title, a specific author, and specific date of creation. This is a way to carry on also the metadata about the extracted smells. And moreover, especially when we have an automatic extraction, and we have actually most of our knowledge graph has been automatically extracted, we extract also the software for which we use to extract this information, and also a confidence score that the machine gives, so that we are even able to filter out the results that are not precise, that are below a certain threshold. So all this effort produced a data set of over 100 million triples. That is quite big actually now, and is still a bit growing until the end of the project that will finish in December. This over 100 million triples represent more than 2 million smells, okay? Coming from over 7 million textual resources and sentences, and over 70 paintings, basically 70,000 paintings from the different collections. So this knowledge graph can be reached and assessed in different way. A part of the ontology, of course, is public, and there is also a larger presentation about this. The vocabularies are available at this address, and the knowledge graph is available at data.odeuropa.eu, so it's possible to query it and to observe all its to get all the information in different formats. And for the ones that prefer not to use queries but to navigate in the browser, we have also a demonstrator that is basically a data explorer. So at this address, explorer.odeuropa.eu, we expose the whole collection that we processed. And it's possible to navigate the different smell sources, see the different aggregated results, and also to search for a specific smell source, smell carrier, quality, emotion, etc., and assess the database of images and text that we processed. That's all. I take also this stage to, for people that are interested in this kind of thing, to tell that in November 28 we do a smell culture fair in Amsterdam. But for the rest, feel free to look at our website, odeuropa.eu, and to see everything also from that side. Okay, thank you for the attention, and happy to discuss with you.
All right, so I'm Jacopo De Berardinis from King's College London, and I'm the representative for the Polyphonia project, which we introduced before. Here we'll try to give like a quick overview of the knowledge graph in Polyphonia, and then we will focus in particular on two knowledge graphs, so Choco and Armory, as we will see very soon. All right, so Choco is the core corpus, is a knowledge graph of 21,000 harmonic progressions from annotated collections, and we will have the opportunity to see specifically what the dataset contains. Armory is instead the harmonic memory, is a knowledge graph built from Choco by extracting harmonic segments and harmonic similarities. And again, we will have time to discuss Armory together. Then we have meetups, knowledge graph for musical encounters in Europe. Oops, apologies for the typo. From a specific period and including 33,000 biographies. And I will leave the links to the resources. Then we have tonalities containing MEI scores and analytical interpretation based on the different musical theories which were modeled in the Polyphonia ontology network, according to the Pretorius and the Zarlino theories. Then we have tunes and patterns for folk music, in particular folk tunes, tune families, melodic similarities, and melodic patterns. Regarding instrument, we have the organ knowledge graph containing information, very detailed information about 2,000 touch pipe organs from encyclopedic and web resources. Similarly, bells contains data regarding 88 Italian bells, bell tower, bell singers from the General Catalog of Italian Cultural Heritage. And finally, the mods concert is a knowledge graph providing information of about 80,000 concerts intended for broadcast on the Dutch public TV and radio broadcasters. So this is an overview of some of the knowledge graphs developed in Polyphonia. We will not have time to focus on all of them, so we will be basically looking at Choco and Armory. Of course, there are more information that can be found from Melody, which is like our system to create data stories using Sparkle queries. So you can already see some statistics regarding these knowledge graphs. And then the web portal, which is similar to what Pasquale was presenting before in terms of exploration of resources. So without having any expert knowledge behind our resources, you can easily navigate the knowledge graph in Polyphonia. And it's work in progress in the sense that the portal is up there, but we are still working on reconciling all the knowledge graphs to make sure that the data comes from the different pilots and from the different knowledge graph. At the moment, it contains like some preliminary data for the evaluation of the portal. Okay, as I was presenting before, Choco is the core corpus. It comes from an integration workflow to integrate harmonic annotation from 18 datasets, and this is high quality data because it comes from human-made annotations. So 18 datasets, 14 formats, 9 notation, and in total we have 21,000 chord annotations, so chord progressions, essentially. And this is an overview of the pipeline, which generalizes not only for chord data, but also for music annotation in general. So music annotation covering, for example, segments, music emotions, music patterns, pitch estimations, like everything that can be annotated on the musical surface, on the audio and on symbolic music, can be aggregated with this pipeline. So the first step essentially consists in the creation of a GEMS dataset. A GEMS is a format which is used in music information retrieval for releasing music annotation data. And this is achieving a level of interoperability at the annotation format level. Then we have the converter, which takes a GEM dataset and create interoperability at the level of musical notation. This is because music chords, as well as other music annotation, can be expressed according to different notations. And this is how we are bringing all the notations together. And finally, we use Sparkle Anything for generating a knowledge graph from a GEMS dataset, which has been extended with information from the converter. This is a specific overview of the formats which are currently supported by the gemifier, so achieving the interoperability at the level of the annotation standards. As you can see, there's like CSV, TXT, Roman text. These are general and specific annotation format in music information retrieval. And this is an overview of the converter instead. So achieving interoperability at the level of the music notation by bringing together different families for expressing harmonic information. And finally, this is an overview of the music annotation pattern behind the SmashUp ecosystem. So this is actually how we achieve the interoperability of music annotation once it is released as an integrated collection. And the music annotation pattern is one of the ontologies in the polyphony ontology network. So by using Sparkle Anything, the GEMS dataset, and the GEMS ontology, we can easily create knowledge graph with a simple Sparkle Anything query, as you can see from this slide. So this is an overview of the dataset integrated in Choco, where you can appreciate the diversity in terms of original formats, notations, annotations, and genres. So at the moment, we have information about chords, we have information about keys. We also have structural annotation and beat annotation, which at the moment are not present in the knowledge graph, but are present in the GEMS dataset. We also have identifiers and many, many statistics regarding this collection, which can be found on our GitHub and on our Melody story. As I was presenting before, we also have links to other resources. So the MIDI link data cloud, which gives information about the MIDI files of musical pieces, but we also found links to experiences in the listening experience database. So allowing users to relate harmonical content to emotions, memories, and feelings. And this is like a table with the links to the resources, including the GitHub, the endpoint, some queries, and the maintainers. So we move from Choco to Harmony, the harmonic memory, which is an interesting case study of how we can use all this information coming from different sources. So Harmony is a collection of harmonic patterns, or better, harmonic segments, which were reconciled into a set of families of harmonic patterns, and the similarity expressed among all these patterns. So this gives us the possibility of creating tools and resources for computational creativity, for example. So we are aware that generative AI systems at the moment, for example, have a tendency to replace artists in a way, or at least this is kind of getting dangerous now. There are ethical concerns. There is lack of accountability, explainability of these solutions. and also musical plausibility. And the harmonic memory is a proposition for actually allowing the creation of systems that can leverage the diversity of data and the traceability of our methods from the data itself. So the harmonic memory essentially creates patterns through music information retrieval methods. So here is a way of using musicological information to create visualization that are useful for the segmentation of music. So harmonic progressions are broken down into musical segments. Musical segments are compared to each other using definitions of harmonic similarity. And finally, the knowledge graph is created to preserve all this detail and fine-grained information. We are then able to address use cases for pattern discoveries. So for a given pattern, which are the tracks in which the pattern can be found, or which harmonic patterns are used in Michelle by the Beatles, but also in a classical composition, or which tracks include a dominant cycle in 7 steps. So pattern discovery as a way of doing information seeking, but also finding variations. So given a chord sequence, which are its variation and which tracks these variations belong to. And finally, something which is more towards human-machine generation, so to connect what we were saying before regarding use cases for generative AI. We can create a progression started with Come Together by the Beatles, continuing with a segment found in a rap song, and then continuing with another by Chuck Berry and Elvis Presley. And this is an overview of an harmonic progressions, which is resulting from the combination of these musical ideas from these harmonic segments. And yes, this is a link to the resources, so the GitHub, the endpoint, example queries, the article, and the maintainers. I conclude the presentation with some challenges which we found in the Polyphonia project, and I've seen already some interesting solutions from the other projects. So the first challenge is regarding the interoperability of the musical resources that necessitates common ontologies. The second challenge instead, how to account for provenance, for integrating knowledge graphs, and finally, data reconciliation issues through entity alignment, which is definitely not trivial and difficult to scale. Thanks again for your attention.